to which range you can scan actually, or you can maybe it's sometimes scanning is not the fixed wavelength you can fix, but it's a scanning of some range. Usually the maximum range we can cover 400 to 4000 centimeter inverse, not like all. Rotational transitions have small energy differences. Okay, how much? Less than equal to 100 centimeter inverse. So there is a different type of transition is possible, little small energy difference. Vibrational transitions occur at higher energy. Then rotational vibrational transitions combinedly often occur together. So there is one picture actually. This picture you can see. So one vibrational level there is a much more energy gap, but within this vibration there is some rotational energy. So if there is any stretching, any absorption, molecules show both the simultaneously. Vibrational transitions and rotational transitions are simultaneously. So what is the field rotational energies? Electrons are going to the upper and lower. Okay, this type of. So this is some schematic diagram for a oscillator. Potential energy resembles classical harmonic oscillator. These are actually some schematic diagram to understand the difference between the rotational and the vibrational transition level. So these are V0, V1, V2, V3, and these are R actually. And you can understand the lots of rotational transition levels are incorporated within the vibrational level. Okay, so it's not possible without rotational transition changes the vibration transition possible. Now for organic molecule, what happened? More sharper bands and distinct spectrum than UV visible. So we actually we in the first slide you observe that there is some sharpness appears of band peak, but in UV visible spectroscopy we have some broadness, and from there maximum absorption lambda max can be calculated. Not for a one pointed peak is there. We from the broadness of the peak we try to found one lambda max. Okay, and that is their actually parameter, identified parameter for UV visible spectroscopy. So, but here we see the sharp peak. Sometimes it's contaminated or split depending on the other chemical environment, but usually its sharpness is there. Fluorescence or phosphorus, UV visible fluorescence, phosphorus, all are lambda max related and exceptional for optical isomers. If there is optical isomers, some problem will be there because they show same type of things, functionality or etc. There will be some broadening may appear. Analytical tool for compound identification, group analysis, estimation of amount of compound. So this is some also we can use as analytical tool for identification of a particular compound by the peak appeared in the spectrum. Group analysis means functional group analysis, and we can quantify the amount. Okay. Spectra shows percentage transmittance that I already mentioned versus wave number instead of lambda like UV for convenience. Now, type of molecular vibration. Okay, we this is something we actually, this is like some, this is atoms, a nucleus, and there is some, suppose you have H2O molecule. Okay, so oxygen and two hydrogen, then how they actually, their mode of bending, their mode of vibration. So basic from the right left hand side, bond stretching, simple stretching, how it's possible. These are one fixed and they are like vibrate up down up down. This is one thing, and this is symmetric. And another point, one is up down in that region, not in the same direction, both are performed actually. So there is a asymmetric thing. You can see by understand this one. If it's coming down, then it's up. So the directions of vibration is different. This is the most important stretching actually. Sometimes the other, which I mentioned in the bond bending, these also sometimes show some for a particular functional group. They are maybe more prominent than bond stretching. Usually these are main actually. Now bond bending. So there is a lots of way bending. So bonds are not in particular position, they are somewhat twisted now. So in plane rocking, so it's going try to going here, you try to coming here, but and they are oscillating in this way. So it's like twisting type, rotate and coming back, two at a time. Okay, so this is some difficult actually. You can check this visual image. You can go to this bond bending video. There is there in the YouTube. You can find. So from there you can get clear idea about this plane rocking, how the molecule twisted. Now this is in the two different way. Now same direction they are rocking, but scissoring they are coming to each other and coming back, coming to each other, close to each other and apart, coming and going, and according to it twisted actually. This bold one. So this is plain scissoring, like our scissor, and this one is something some theoretical aspect, but you can see this is plain wagging and this is twisting. So this is happened, so they are actually vibrate their own position. So suppose it not vibrate, it these two are vibrations in mode. So, and another point, so that they can be actually so vibrate, there is generate some absorption. And another point, if this vibration there, but it's not vibrate. So some and not equal something is there. Okay, and as a whole, there is a all absorption energy is different for this inequality of these two. This is omega, this is tau, this is out of plane twisting. So suppose one bond is vibrate in not actually rocking or scissoring type movement vibration. They are vibrate their own position. Okay, understand? So these are some schematic diagram for this bond bending. So bond are So these are bond bending situations and these are bond stretching situations. This is stretching means they are try to coming out or coming in. The situation in both the coming try to coming out stretched condition. So that is symmetric and asymmetric nature. Okay. Now this is the mode of vibration where absorption because of this vibration in a particular molecule absorb a certain amount of energy. Now, number of vibration mode. For non-linear molecule, number of vibration is a 3 capital N minus 6. But linear molecules, number of vibration 3n minus 5. Okay, so that means one is less because if the asymmetric in the lengthwise, so they are if a positive and negative direction, it's actually sometimes it cancel out. So that's why Cn minus 5 for linear molecules. Non-linear have the same whatever I mentioned in the previous slide, that is actually non-linear.
Ma'am, what is N?
N is the number of molecule. No, not number of molecule, number of atom.
Atomicity.
Okay, ma'am.
Atomic. So cause of more number of peaks in IR spectra and observed vibration can be less than predicted. Okay. So what is this meaning? Cause of more number of peaks in IR spectra that is, so there is some different type of other than molecule may be in presence of this too. Okay. So symmetry, no change in dipole moment maybe. Okay. And for energy of vibrations are identical. That to if the molecule is symmetry, then IR peaks may be more, but the absorption is more, but the observed vibration, what we predicted, is always less. There is a fixed number of vibration or etc. Suppose you have CH vibration. There is a lots of CH vibrations, but depending on the chemical environment, you will get IR spectra. The peaks are different. Maybe from aromatic, maybe from aliphatic, but the vibration type is maybe more or less same. Suppose you have aliphatic CH3 and CH2. Okay, the vibration CH vibration is all, more or less same, but their peak is different position, but vibration is same. That's why vibration pattern will be maybe less, but the peak will be more. Okay, so that is some region actually, and I mention here dipole moment with respect to dipole moment. The symmetric element or etc. They have same type of vibrations, but higher spectra give the peaks depending on the chemical environment. Okay, these are different. Now energy of vibrations are identical. That is also I mentioned. No, the CH3 and CH2 both have same energy vibration, but their appearance in the IR spectra is different. Okay. Now, and absorption intensity has sometimes the so much less absorption, the vibrations cannot be actually recognized, but reflection you can see in a low absorption intensity. Frequency beyond range of instrument. That is also possible. Suppose I already mentioned 400 to 4000 is normal. In our instrument is 650 to 4000 centimeter inverse. But sometimes maybe 4 to 600 there is a vibration, but we can't able to see. Now, in order to molecule absorb IR spectra, vibration at same frequency as in light must have a change in its net dipole moment. That is important as a result of the vibration. So, in order for molecule to absorb IR radiation, that is the criteria. Okay, vibration at same frequency as in light. The vibration should be in the same frequency. Okay, resonate to in the in presence of that light and must have a change total dipole moment, otherwise it's not called the IR active. Okay, now for example we took one HCl, so you can understand the, from the beginning of two lines, this is -5 linear, so one mode, and there is carbon dioxide, there is a 4 mode. Linear is one mode, and there is a, this is the simple calculation for the checking the number of vibration modes involved in IR during the IR. Both are IR active. For carbon dioxide, what happened? It is IR active or not? Is linear. ACL is a, I definitely have net dipole moment, but what happened with the carbon dioxide? Hmm?
No dipole moment.
No dipole moment, but here I am showing. Because different modes are there, 4 modes are there, all are not have like this. So one by one, HCl one mode like this way. Carbon dioxide 4 modes, these are inactive. Okay, but this one, this is IR active. You can understand this one, this vibration mode is, this is also IR active, this is also IR active. So carbon dioxide, though it is linear, but still one is plus minus is negative, but other 3 is IR active. There is some net dipole moment is not 0. Is clear? So all linear molecule that doesn't mean have 0 dipole moment and uh, gives the Symmetry also, there is a symmetry also gives zero dipole moment and IR inactive. That doesn't mean. We have to verify their modes, how they vibrate. Then we can conclude. If the overall overall vibrate, there is a net dipole moment not zero, they are IR active, and we can get the IR spectrum. Clear at this point? Hmm. So this position is the last, this twisting. So these are not vibrate at all actually. They are vibrate their own position. Okay. Now, this is some actually instrumental setup. The principle actually little bit. Uh, we don't need so much, but I want to show how it actually the instrumental setup, because I know though you are in Btech student, IR is now a big use in different sector. Maybe not for IT, but for any characterization technique, solid or liquid or any state for any material, you can go the FTIR and you will get some important information about the functionality. That's we definitely need. Because if you don't know the functionality, what type of molecules are there, functionality means hydroxyl group or aldehyde group or keto group. Huh. In such a situation, so that predict how they behaves further. If there is a polyhydroxy, suppose we have hydroxyl group, that means there is tendency to dissolve in water. So you make one polymer. So just go for the, because polymer are not soluble, so just go for solid FTIR. NMR are complicated for this polymer, but FTIR at least predict the nicely the functional group. Okay, and you can understand the nature of polymer. So how the nature of polymer depending on their functionality, and now you can identify their behavior for a particular application. Okay, so maybe in electrical, maybe in mechanical purpose, corrosion purpose, or rigidity purpose, you can get a nice idea from the FTIR. UV doesn't go like this way, but FTIR is a very important spectroscopy. Okay, NMR is too, but sometimes in situ you need. Suppose you need don't you can go for the deuterated solvent. NMR have problem. You need deuterated solvent. Still solid NMR is not like that, and sometimes solid NMR not give provide very nicely the functionality. Only the proton or carbon position, but FTIR you can get. So that's why it's very important. And I just little bit idea about the instrumental. Obviously, there was one M1 and M2 two mirror sample. So what is two beams having equal intensity formed from light source after splitting by central mirror. There is one mirror, okay, and beams go to two other mirror reflected by central mirror, recombine and pass through sample to detector. Okay, pass through sample to detector. There is some reflection. So what is there is different light source are going from mirror to mirror to mirror, reflection, etc. As a switch off, if anybody have been not in a switch off means mute yourself. There is one sound actually. Mute yourself. Two side mirrors, one fixed and other movable. Two side mirrors, one fixed and other movable. These are movable, one fixed. Two, then a movable, the move second mirror, light in two parts, travel different distance before recombined. Okay, and construct and destructive interference. As mirror is moved, get a change in signal. So that is a highlight actually. This arrangement actually gives a phenomena, gives a light phenomena interference. Okay, this will actually we need to produce the IR signal. So interference of light. This is, if destructive and constructive. If there is a constructive stretching frequency or matching, you get a nice big signal. If destructive nature, you will get a destructive intensity is low. So this is actually the mirror setting and infrared light. Light is in a range in infrared, and after that the mirror arrangement trick the instrumental. Mainly mirror are doing change. You can change the distance. One is movable. Depending on this, you can get your IR. So there is actually, I will give you this presentation. If you want, you can little bit know. This is the physical part, but is not one slide is actually sufficient. So just for your purpose, if you need, I just keep it here. But I am not explaining so much things. Then I have to go for the interference of light and etc. But these are important for you clarify yourself. Okay, just a trip, just a actually give a some slide to that's you will go for reading actually. Now, advantage of FTIR. Okay. So now I am actually from the last slide, I am telling about the FTIR, not only the IR. So what is the difference of FTIR and IR? Actually nowadays we are going for IR on FTIR, not the IR. So I may actually change little bit quickly. FTI. FT means Fourier transformation. Okay, some mathematical solution to make the signal more clear. Okay, so we put this thing in our software actually, and we will get something, some modern versions or more prominent version of peak. So that's the actually advantage of FTIR, much faster second versus minute. So it's second, in second we can get, and it's take only IR takes minutes to produce the spectrum. Use signal averaging to increase signal to noise. So it decreases the noise ratio. And from this picture, okay, this picture you can show noise is 9 units, signal is 14 units. Okay, now it's 1. This is only 1, noise is to this signal ratio 1, it's 4, then 16, 64, 256. So this is actually nice peak. So this is actually covering with the FTIR. So that noise is minimum in our spectrum. How much less the molecule, we get a nice we can try to get nice spectrum without any noise. These are not sufficient to understand that which one, this one and this, there is also one peak, there is also one peak, no doubt, but these are noise or peak that is not clear from this first one. Okay, but here we can, this is a hum, this is a hum, this is a hum. So this is at least one peak you can identify, but not in a, there is not in any noise. Whatever the peak, it's coming. Higher inherent S by A, no slits, less optical equipment, higher intensity. So that is some some actually technical term. Higher inherent S by A, no slits. This peak appearance actually. Joto SN increase hobe, then we will get some sharp peak that I mentioned already. Less optical equipment, higher light intensity. So optical equipment we need actually for this one, higher light intensity. Intensity of light we need in higher, but the optical equipment, this is the instrumental, is not so much the insight of this other parameter, like this is for FTIR actually. So FTIR need the mirror, sufficient nice mirror, higher intensity, go for the S by N higher inherent. Okay, and we get the sharp peak. High resolution that we already predicted, less than zero point 0.1 centimeter inwards. Resolution is also high. So visibility actually. Disadvantage, single beam requires collecting blank. Single beam, it actually work with higher intensity. And what happened? Collecting the blank. Blank means you need first a solvent. Okay. Otherwise, solvent combined with your, if in your sample is in solvent system, solution, you will go in with solution, you need blank. Otherwise, you need blank with respect to air. First run the compound because there is a carbon dioxide, nitrogen, etc., and make it zero. Then go for the analysis. Otherwise, all peaks are coming in the eye. That is in be very sensitive. No? Within a second, it can give you. So that means you have to any moisture also give a response, hydroxyl group response. So initially in the working condition, working environment, you just go through one blank run and make it zero. Okay, so that the oxygen, moisture content, nitrogen peaks and carbon dioxide peaks in the air are not combined with your spectrum. That is important. Can't use thermal detector too slow. That is instrumental sometimes. Okay, so it's like some mathematical detector. After that, we use some software, Fourier transformations, to multiply the signal to noise ratio, suppress the noise by this ratio, and collect the data. So obviously, we can't use here any other detector. Only we absorb the frequency and put it in a Fourier transformation software. Okay, so if the computer is not working, you will not get any other way to detect the frequency actually for FTIR. अच्छा, in a very conclusive few lines, in normal IR, scan through frequency range, and if FTIR collect all frequency at a once. So it going to in IR, what happened? It going to first 400, then 500. This slowly moving and scan the molecule slowly. Actually, that's why it takes some time. But FTIR, it overall all frequencies are there. Suppose from there, system is like that, higher intensity with all frequency. Whatever the frequency for a particular transition needed, they catch it and they show the their responsibility. They Okay, so all frequencies there in a higher intensity, according to their functionality, they observe and show the peak instantly. Don't wait for running. Suppose you have in instrument, you run first 400, so it increase, say then it increase, then it increase with a particular gradient. So that is not the way for FTIR. That's why FTIR is a very fast. So that is few points for advantage why we're shifting towards the FTIR. Now all are FTIR. Whatever we run the sample in our all instrument are FTIR because it's a very fast, very sensitive. Okay, and you can understand, we can get a within a second a very nice peak for particular functional group. Now applications of IR. So qualitative analysis for the identification of compound and prediction of functional group by looking at group frequency region. So actually this is the group frequency region, minus 3600 to 1200. But we always try to 650 to something. But there is one actually 500 to 800, some important region we will go later. First, we can see single bond stage. So this is single bond stage, this up to 2500. And this is for OH, NH stage and CH stage. Now, for triple bond, nitrile or carbones, okay, all are from 2500 to 2000. Double bond region are this much. 200 to 1500, 2000 to 1500. Then fingerprint region, skeletal vibration. That is important. Actually, we measured the fingerprint to 400 to 500 to 800 actually. Okay. So there is a different type of bond frequency with their environment also bending, etc. We can get a particular analysis part actually here. You can see different, much more peaks are here depending on their nature. Particular. Suppose you have acetone and you have ethanol. The fingerprint region will be different. Okay, only bending bonds there, and you can already show there is a different type of bending vibration, actually, bond bending vibration. These are appear in this region mainly. Sometimes they are very special for a particular compound. We can explain all the time which stretching or bending vibration is responsible here. Okay, stretching we can identify, but bending is little bit complicated because of four types are there. It's very imaginary one. But their appearance, repeated appearance from the standard sample, we can know the acetone have this region is a fixed vibration. So maybe this. So by understanding of the repetition of the sample, we can go for the reference and we can assign for the peak for the acetone like this way. Group frequency. Okay. Now group frequency from OH or NH are 3000 to 38 and then 3800. Then CH. I have one chart also from there, from later on. And there is a triple bond, double bond, carbonyl group. Then NN, there is a different type of pi bond and triple bond are here in this region, and also some bending here. Whatever I have mentioned, just one uh, actually schematic diagram. This is actually the last point, initial guide to compound identification that we need. Okay, but not positive always. That is also I write down because sometimes depending on the environment, maybe there is some resonance. So initially we think this is triple bond. Actually, because of resonance, they behave as double bond, and the IR shows a different structure. Okay, so that is some trial error, or by NMR or UV run, we can understand slowly, but not always for unknown sample. So these are listed, probable, and tentatively almost correct the frequency range for a particular functional group. Strong, and I write down as possible medium, strong, whatever. Sometimes it variable that depending on resonance actually variable. So these are most actually important. Usually we identify first these things in our IR spectra. Whenever we got the IR spectra, we try to found this one. Okay. Suppose you have carbonyl group, C double bond O, aldehyde, ketone, carboxylic acid, ester, all have. Range is 1690 to 1760. Strong peak in between this. So that means it's there is a carbonyl group, C double bond O group. Okay, maybe from ester, maybe from E. Later on, the other chemical testing or NMR we can establish, but carbonyl group is there. So nature we can understand it. It will give some test. Okay. Now fingerprint region, 1200 to 700 centimeter inverse. Region of most single bond signals pattern characteristic of overall skeletal structure of a compound, complex and unique. Okay, so what is the point? I just repeated. These are the fingerprint region. You can see this green part. You have acetone and you have methyl acetate. Both are different, but more or less this part is same, or at least CH3CO part is same. But you see this region have marked difference. So from observing this, we can very uh, nicely can predict that this is for acetone, because we know acetone, what whenever you get the acetone from lab, from any bottle, from different lab, you will get the same region with along with the peak. So this spectra is fixed for acetone. If you have a standard and you run the sample, though there is some contaminated peak will appear, but if there is no, like the fingerprint is same, or you can understand this is acetone or ethyl, both are volatile. Maybe smell is little bit forester, but still then you will go for the eye. So you can identify if there is no mark for the bottle, still you can identify it using the FTIR. And now this is the carbonyl peak C1715 and here 1735. Okay, and CO peak is here. CO peak is 1250 centimeter inverse. This one. So there is a in the 1250. This one is a 1250 peak and 1000. Two peaks are there. One is 12 and one is 1000 actually. So these are actually some pattern we have to conclude, or now you have some explain why type question, why this peak is appear here, what is the role of resonance for the IR spectroscopic peak appearance. These have this type of question you have. What is the problem if you have 6-member ring to 5-member ring? There is any frequency lower or higher? This type of question will go. First week, this one. So there is a oxygen, hydrogen, nitrogen, hydrogen, carbon, hydrogen, and triple bond. You can understand the values 13400, 3400, and here is a 3000. And again, here triple bond. This carbon carbon different bond, different nature. This is single bond carbon oxygen 1100. Double bond carbon carbon, you have 1650. C double bond O. So that is C double bond O and C triple bond. These two actually C triple bond N and C triple bond C. Both the values are changes. What is the reason for that one? The values. What is the reason? Suppose you have this one, triple bond C, triple bond N, and C triple bond C. What is the reason?
ম্যাম সি ট্রিপল বন্ডে এনার্জি বেশি, বন্ড এনার্জি।
দেন কিভাবে সেটা বার করা যাবে? মানে ফ্রিকোয়েন্সির সাথে কিভাবে রিলেশনসটা আছে?
ম্যাম ইনভার্স ই এনার্জির সঙ্গে তো ফ্রিকোয়েন্সি ইনভার্স রিলেশন।
Frequency wave number equal to there is a 1/2 pi by 1/2 pi root over something is there. Do you remember this equation? Bond strength, the reduced mass versus wave number. This type of question will appear. I will first you will go through the this IR, then we will go for the questionnaire. Okay, understand and see the. That's why I am showing. You are looking for this one. Why this happened? Suppose you have a C double bond O and C double bond C. Difference is wave number. What is the reason? Frequency is wave number is less. Wave number is higher. Then what happened? They have less reduced mass or higher reduced mass. That we have to identify actually. Okay, so this will suppose this one we will explain later on, but for your interest actually go through the Pavia book, you will get this thing. There is a allen, there is a one this type of molecule, 3-member, 4-member, 5-member, and just one, and then again we will have a 6-member. If values are different, wave number is different, frequency or centimeter inverse is different, then what is the reason for this Same. They all are C double bond C, but still the values are different. What is the reason? Exo double bond. All are exo double bond. All are exo endo double bond. So next we'll explain this type of some few question actually, but presentation mode is not enough. So whiteboard I will use actually for this type of question. And I have another part pending because it's easy to give the session the aromaticity. So next day I will cover there is lots of actually thing. For example, we'll suppose you have carbonyl group. See the range of carbonyl group. Then this is something difference. CH3, CH3, and there is a so there is a resonance obviously. This part. These are from your question actually. Okay. This type of question distinguish this molecule with the there is a benzyl. This one is a benzyl, and this is a 1,4 just simple carbonyl, 1,2 diketo compound, aliphatic, butane. So why this happen? One is a resonance bond are so C double bond O bonding is less strong because of the conjugation. That's why energy less, frequency number less. This is not like lambda. Lambda is inverse, but here is total is different. If wave number less, that means energy is less. Okay, because energy versus mu bar. So next day we'll go for this type of question. Very interesting. But you will see the Pavia just browse, then we'll go. And along with the aromaticity. And there is another compound, keto tautomer and enol tautomer. What is the content? You can identify by their bond, whether it appear as a keto or enol. So this is something we'll go for. This is from your question pattern actually. This is the answer actually. But question is like that. How you distinguish keto tautomer to enol tautomer. So you have to write down that here is a symmetric stretching 1, 2, 2, 3. Here is a doublet actually. These two will symmetric and asymmetric, but because of 2 keto. But here is a hydrogen bonded 1622 centimeter inverse, another on which will come 100 bonded, that is in 32002400 centimeters inverse. So that is your answer. Question I will accordingly question will set up actually. This is some example. So next year we'll go for we'll go for this different type of questions. Role of resonance in the IR, inductive effect, or any other ring member size for the carbonyl, the role of staging frequency of carbonyl group with respect to different functional group. Why this happened? Okay, so answers are there, but we have to explain. Explanation we will tell later. First, you understand the initial part and what is the role of bond strength in bond stretching. That is, resonance decrease the bond strength, so its frequency is lower. You think about this thing always. Okay. So this is also all are from these examples. The question will distinguish actually all how to distinguish butyl butyrate. This is ethyl butyrate. Okay, methyl acrylate and methyl benzoate. Let's see the changes. So you have this ethyl butyrate and vinyl acetate. You can understand. So this is a double bond appear actually. So all are this from this molecule will go for sometimes this question. So that's why I put here this molecule actually, so that you focus on this molecule for during your study. This is some, these are now we will not provide actually, but initially we provide this and tell you describe the peak, important peak for the compound. There is a benzyl aldehyde. So you see aldehyde peak are coming here, CH. But P2CH is coming here. Then what happened? This is some WW for aldehyde. We'll see, because carbonyl group is a keto or aldehyde. That's to be clear. Can be clear by FTIR. So up to this. Okay, but this is a very basic. FTIR not so simple. It's very difficult. Understand. So just a preliminary idea. I will share the slides for your initial whatever I am saying, so that you can reflect, think, and go for the Pavia. Okay, any book, not for Pavia. I'm just sharing. That's why I'm telling. So okay. So next step.
Ma'am, I have a request.
Well,
Uh, Ma'am, if you show us some question, like what kind of question we get in our exams from this,
oh,
it will
FTI,
be
yeah, next day
helpful.
we will go to this actually. Next day we will go to this question pattern and explain both time. Just molecules are here, but it's still not a question there. So we will discussing about the questionnaire from the FTIA, and also I have few pending which I am expecting actually finish this difficult to understand from the PowerPoint presentation. So next day we'll go for the whiteboard presentation, so we can draw and we can clarify this thing. So suppose
Okay,
we
ma'am.
have, uh, so next day we have some interactive session. You can tell me and I can show you the molecular, their resonance, etc. PowerPoint is not sufficient, no, writing purpose. So this is
Yes,
what
ma'am.
principle.
Yes,
This
ma'am.
is like principle I share. So next class we'll go for the pending classes. I have also SN1, SN2, SNI. That both are all are very comfortable to show you in presentation, not in this PowerPoint mode. So I have to complete this. Okay, and let just first start with the aromaticity, then SN1 and SN2 and IR. But you finish your IR first.
Okay, ma'am.
Reading. This SN1, SN2 you know, but for exam purpose I have to tell you. Okay, but I have to tell you, no? Some recording, what is the pattern of question, that we will discuss later on. But this FTIR in the finals. Okay.
Okay,
But
ma'am.
principal I mentioned because after midsem we have hardly 1 month, okay, for the final sem, or 1.5 month maybe. So that time we have very difficult to finish the course. So FTIR questionnaire maybe later on we can do, but FTIR will finish. But NMR and polymer, and there is stereochemistry also is there. So lots of things are for final sem. Hmm. Okay. Achha, Shreyas, hello. Where is your CR? I already sent your syllabus. Okay. And so I forward today also. You can to Shreyas. So Shreyas distribute. Okay. So I stop my class for today.
Yes, ma'am.
Thank you, ma'am.
Thank you, ma'am. Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Maybe
Thank
I
you,
will
ma'am.
send you the class
Thank you, ma'am.
assignment.
Thank you,
Then,
ma'am.
Ma'am,
hmm,
ma'am, where you will send the class assignment?
no, I will create the classroom. Then I will send there.
Okay, ma'am.
Still, I will not create. Okay, you have to accept. So
Okay, ma'am.
classroom I will send, and because I need in two purpose, one for class assignment, internal assessment, and one for your practical purpose too. So that's why I will prepare. Will make one classroom for you create, and then I will send the link. Accept, and immediately for the UV I will send this. I already mentioned from UV I will give you a this week I will send the classroom link and assignment. Okay, but you have time for classroom submission of assignment after mid sem 2 you have, but don't delay. Okay, sometimes you forget to submit because
Okay,
of
ma'am.
pending. And last before our uploading the marks, we have to call the CR and request CR. Last year this happened actually. Request CR in a very bad tone to submit the assignment. Otherwise, sometimes it's very difficult to pass. No, so that thing, that nature actually, you should not have.
Ma'am,
Whenever we put the assignment within 1 week, we submit, whatever the deadline. Maybe someone is some problem, medical problem, family problem, or any other problem. They can, for them, it's extended a long range of date. But for everybody, I request to say submit within 1 week. Okay, because you have not so much pressure right now. Huh, tell me.
ma'am, please send today's slides to our
I already
CR.
sent. I have already sent the course material to
Okay, okay,
Shreyas.
ma'am.
That's
Okay,
why
ma'am.
I'm asking Shreyas, have any problem in showing the things that want to I know. But I already sent the slides, meeting link, meeting recording, everything to Shreyas.
Okay, ma'am.
Okay. I have everything, so no problem. I will send you again. But I think he will distribute you. I send him everything up to
Yes,
date.
yes, ma'am. He gave us the previous day slides. So
I think you ask him. I now I am quite okay. I have not posted initially. The change of the charge handover for HOD. I have little bit busy, but now it's okay. No problem. It's just 1 month,
okay, ma'am.
so I am habituated. So I will whenever come, I will send to you. Recording will come for within maybe sometimes it takes 1 day if there is any problem. Otherwise, coming within 1 hour or 2 hours. Immediately I will send. Okay.